This section traces how a wrong physical theory gave birth to the right mathematical primitive. Kelvin, watching Tate's smoke rings, reasoned that if vorticity is conserved in a frictionless fluid, then the knottedness of a vortex loop can never change. A quantity that cannot continuously deform is naturally discrete and immutable. The physics was false. There is no ether. But the move is the book's seed. Topology is what makes states robustly conserved and quantized where one would otherwise reach for energy. Tate's failed. Periodic table of knots founded knot theory instead. The same conserve the topology instinct returns as topological matter a century later. Predict the whole book from here. Wherever states must stay discrete against every smooth perturbation, look for a topological invariant holding them there. This first section explains how topology entered physics, and it does so through a wrong idea that refused to die. Kelvin guesses that atoms are knots in the ether. His circulation theorem conserves vortex topology, so a knot type is immutable, and immutable discrete types are exactly what the chemical elements demand. The physics is false. There is no ether, and there are no vortex atoms. Yet, the guess forces Tate to catalogue every knot, and knot theory is born, barren for its target, but fertile in itself. That decoupling is the chapter's primitive for the whole book. A hypothesis can be false as physics and generative as mathematics, the two properties independent of each other. The mathematics it forces into being outlives it and re-enters physics a century later, as the author notes, for entirely different reasons. This section explains what a knot invariant is and why physics turns out to evaluate the same object. A knot invariant is a quotient made mechanical, a rule map from a tangled diagram to a number, rigged so that any two diagrams which deform into each other without cutting land on the same output. Sameness of output cannot prove equivalence, but difference proves inequivalence. The map sees only the topology, having forgotten all geometry. Kaufman's is the minimal worked instance. 2 local rewrite rules grind any diagram down to a single scalar. A bare loop becomes D, and a crossing splits into its two uncrossings, weighted A and A inverse. The chapter's real payload, the hook for the whole book, is that nature evaluates this same quotient. In a topological phase, the quantum amplitude of particle world lines is a knot invariant, depending on how the paths braid and nothing else. Variant, depending on how the paths braid and nothing else. This section explains how you tell two knots apart when you cannot simply look at them. You cannot compare two knots by staring, because continuous deformation hides their sameness. So you build a map that is deliberately blind to the deformation, a function that stays constant on each topological equivalence class. Then, different outputs certify inequivalent knots. This is the whole logic, and it runs one way only. Equal outputs prove nothing. The Kaufman bracket is the chapter's worked instance, 2 local rewrite rules. A crossing becomes an A-weighted sum of uncrossings. A bare loop becomes D, which equals minus A squared minus A to the negative 2 power. Grind any diagram down to a single number. The surprising part is that a purely local skein rule computes a global topological property. It is the same quotient, then separate move that sits behind every invariant, and it is the hinge to the physics. Physics. This section explains why the standard derivation of bosons and fermions rests on the wrong foundation. The textbook derivation is wrong, and that flaw is the insight the whole chapter turns on. The step that reads exchange squared equals identity smuggles in the algebra of an operator, when statistics is really the topology of paths. Feynman's sum runs over trajectories that swap two particles. Two such histories that cannot be deformed into one another must enter with independent phases. How many inequivalent path classes exist and how they compose is fixed by the shape of configuration space rather than by the wave function, and hence by spatial dimension. That single reframe is the chapter's purpose. It converts the question why only, plus or minus 1, into the question how many path classes does this dimension permit, and it points at the case where the count is no longer 2. This section explains why exchange statistics comes down to counting and why the count depends on dimension. Exchange statistics is a property of paths, not of particles. It is a representation of the group of topologically distinct paths through configuration space. Feynman's sum weights each homotopy class of trajectories by a phase, and the only constraint quantum mechanics imposes is that those phases compose the way the paths do. Nothing more. In 3 dimensions, that path group is the permutation group, Sn, whose one-dimensional representations number exactly 2, the trivial one and the sign. So bosons and fermions exhaust the possibilities, not by deep law, but by counting. The payload of the chapter is that this exhaustion is contingent on dimension. Change where the particles live, the group changes, and with it, what statistics can exist. This section explains how the Aharonov-Bohm effect turns particle statistics into a phase that a path accumulates, and how binding a charge to a flux tube builds the smallest machine that makes fractional statistics. Statistics is a phase that a closed loop pays. The common picture treats it as an intrinsic property a particle carries, but the truer account is that it is a debt accumulated by a path as it encircles a region. The Aharonov-Bohm effect is the whole engine. A charge that encircles confined flux it never touches still accumulates a phase proportional to the charge q times the flux phi. The reason is that the line integral of the vector potential around the loop closes, by Stokes's theorem, onto the enclosed flux alone. That makes the phase a purely topological debt, path-independent and blind to the local fields. Bind a charge to a flux tube and you have the minimal machine that manufactures fractional statistics. Exchanging 2 such composites yields a phase factor, e to the power I times q phi over h bar. A single knob, theta equals q phi over h bar, sweeps continuously through boson, fermion, and anyone. The chapter's move is that statistics is engineered rather than intrinsic. This is the warm-up whose field theoretic form becomes Chern-Simons theory in Chapter 5. This section explains how every anionic property descends from a single circulation phase. Bind a charge to an infinitely thin flux tube and everything called anionic falls out of one number, the Aharonov-Bohm phase, the phase a charge steals from a vector potential it never locally touches. Now drag one composite around another. The charge circles the flux circles the charge, both contribute, and half that loop is the exchange. So the statistical angle becomes tunable, a boson at 0, a fermion at pi, anything in between. That is the chapter's move. Fractional statistics needs no new force, only a self-consistent composite, and the geometry of the phase already grants it. Spin, fusion, antiparticles, and a torus ground state that knows the anion spectrum with no anion present all descend from that single circulation phase, the warm-up for Chern-Simons. This section explains the basics of Chern-Simons theory. Bind flux to charge by fiat, and statistics becomes geometry. Chern. Simons is the field theory whose action carries no metric, only the anti-symmetric term, epsilon, alpha, beta, gamma, a alpha, partial beta, a gamma. It measures nothing local, only how world lines wind. Its equation of motion staples a flux tube of strength, 2 pi q over k, onto every charge. So exchanging two charges costs an Aharonov-Bohm phase of pi over k, half the naive value because the gauge field's own term cancels the other half. The integer level k is the single dial setting the fractional statistics. Metric freedom is the property that makes the whole thing go. It renders braiding purely topological, which is exactly why this field theory is the paradigm for topological quantum field theory. The object, the rest of the book is built to exploit. M for topological quantum field theory. The object, the rest of the book is built to exploit. This section explains how a field theory that never names the metric turns into a topological quantum field theory. Write an action that never mentions the metric, and it can answer only topological questions. Smooth deformations of space and time leave it untouched. That constraint is almost uniquely binding. In 2 + 1 dimensions, the Chern-Simons term is the only gauge invariant action carrying it. Its equation of motion staples flux, 2 pi over k, onto every charge. Integrate the gauge field out, and the particle path integral collapses to the exponential of I times theta times w, a statistical phase times the winding number of the braid. Exchange statistics become geometry. Insert Wilson loops, and the same machine outputs not invariance. This is the microscopic engine that binds charge to flux, and the book's working paradigm for every topological quantum field theory ahead. All quantum field theory ahead. This section takes a short digression into quantum gravity, and its whole motivation is simple. Strip a theory of gravity of everything local, and what survives is topology. In 2 + 1 dimensions, the metric carries too few degrees of freedom for gravity waves. The vacuum Einstein equation forces flatness at every point, so no point-by-point dynamics remain. Yet nothing collapses to triviality. A flat spacetime can still fold into distinct topologies, and a spatial slice can split, one circle becoming two as time runs. The intractable sum over all metrics thus reduces to a sum over manifolds, and each term is exactly the Chern-Simons partition function of section 5.2. Lower dimensional gravity is a TQFT, and that connection is why topological theories earn physical attention at all. Physical attention at all. This section explains what remains of a physical theory once every local feature is stripped away. Strip a physical theory of everything local and see what survives. That is the chapter's whole move. Quantum gravity as a sum over histories is intractable, so drop matter, then drop a spatial dimension. In 2 + 1 dimensions, the Einstein action has no gravity waves. There are too few degrees of freedom. Curvature is forced to zero. Space-time is flat everywhere. Nothing local remains. Yet the theory is not trivial. What survives is the topology of the space-time manifold, and the surprise is that this residual partition function is the Chern-Simons partition function. Kill the local content of gravity, and a topological theory falls out. This is the historical reason anyone took topological field theory seriously as physics. This section defines topological quantum field theory, and it does so by collapsing a whole quantum theory into a single accounting rule. Cut the spacetime, and you get a vector space. Hand it a filled-in history, and you get a vector inside that space. glued two histories along a shared cut, and the answer is their inner product. Atiyah's axioms are just the demand that this assignment respect cutting. Disjoint pieces, tensor. Reversed orientation dualizes, turning a ket into a bra. Sewing composes. That is the whole of it. A TQFT is what it does to manifolds under gluing, a functor from cobordisms to Hilbert spaces. And topological means the assignment sees only topology, never distance. This chapter is the book's real definition. Everything after is this one rule, worked out. This section explains how a quantum theory can be defined by what it assigns, rather than by how it evolves. A quantum theory need not be specified by its dynamics. It can be specified by what it assigns. Atiyah's axioms fix a topological quantum field theory, a TQFT, as a functor. Each spatial slice earns a Hilbert space. Each spacetime history joining slices earns a linear map, and the structure-preserving conditions supply everything else. Here is how those conditions cash out. Disjoint union becomes tensor product. Orientation, reversal becomes the dual space. Gluing two histories along a shared boundary becomes composition, that is, an inner product. Physics then falls out of bookkeeping. A surface's ground state degeneracy is just z of sigma cross S1, the partition function of the surface times the circle, which is the trace of the identity. Cobordism. The theory is what it does to manifolds. Lagrangian, field content, and construction are all optional. This definition is what the rest of the book studies. This section explains where the Hilbert space of an enneon comes from. An enneon carries no internal state. The Hilbert space lives entirely in how the particles fuse. Write the fusion rule as a times B equals C plus D, and so on. When a pair admits more than one fusion channel, the theory is non-abelian, and those orthogonal channels are the state space. They are degrees of freedom belonging to the pair, not to either particle. Locality seals it. Encircling both particles is the only measurement that reads the channel, so the information is non-local by construction. Dimension counts the consistent labelings of a fusion tree, independent of which tree you pick, and it grows as the quantum dimension raised to the nth power. For Fibonacci enneons, tau times tau equals the identity plus tau, and this yields the golden mean. The chapter's telos is a functor from world line diagrams to Hilbert spaces. The chapter's telos is a functor from world line diagrams to Hilbert spaces. This section explains where a topological quantum computer stores its degrees of freedom. The answer is that they live not in what each particle is, but in the number of distinct ways particles can fuse. Two enneons carry a Hilbert space whose dimension simply counts their allowed fusion outcomes. Abelian theories offer one channel. Non-abelian theories offer several, and those extra dimensions are the entire subject. The surprise that reorganizes everything is locality. No measurement of a single enneon tells you which channel the pair occupies. You must encircle both. Count the fusion trees of n Fibonacci taus, and the dimension climbs along the Fibonacci sequence, the quantum dimension being the golden mean. The stored qubit lives in how things fuse, invisible to any local probe, and therefore topologically protected. This is the substrate the rest of the book computes on. This section explains change of basis and F matrices. Picture 1. Hilbert, space seen through two coordinate charts. 3 anyons A, B, and C, fusing to a fixed total charge, E span a single space, but fusing A and B first, versus fusing B and C first, labels the states of that space differently. The F matrix is the unitary transition between those two labelings. It is nothing but a change of basis, so it adds no physics the space did not already hold. Its whole content is that it acts locally. Applied to any subtree inside a larger diagram, it lets you rewrite any fusion tree into any other. This is literally the 6J symbol of angular momentum recoupling. Combine 3 spins, reassociate the coupling, and you have the associator of the fusion category wearing coordinates. Simon's flag. If you study one chapter closely, this is it. Study one chapter closely, this is it. This section explains why 3 anyons fusing to a fixed total charge carry one quantum space with 2 natural descriptions and the matrix that relates them. 3 anyons fusing to a fixed total charge span one Hilbert space, yet you can build it 2 ways. You fuse the left pair first, or you fuse the right pair first. Same space, 2 bases. The F matrix is the unitary that rotates between them. Its unitarity is forced, no physics may depend on which pair you bracketed. This is associativity, made quantitative, the recoupling coefficient, identical to the 6J symbol of angular momentum addition. Whichever fusion tree you draw is mere convention. The F matrix is the invariant relating those conventions, and any tree converts to any other by applying it locally. The author flags this as the chapter. The whole non-abelian structure lives in how bracketings interconvert. This section explains why exchanging 2 identical anyons cannot be captured by a single number. Exchange stops being a number. When 2 identical anyons swap, the phase they accumulate depends on which channel they fuse to. So statistics becomes a whole family of values, one for each fusion outcome, written R carrying 2 upper labels both equal to A and 1 lower label C. The channel they fuse to. That single move, plus 1 bookkeeping trick, generates everything. To braid a pair that is not already in a definite channel, rotate by F into the basis where their fusion is sharp, apply R, then rotate back. Braiding any number of identical particles reduces to 2 pieces of data composed together. The first is R, the exchange of a pair whose channel is already known. The second is F, the change of basis. Compose those 2, and you have the whole thing. The chapter installs the atom. R. Every braid representation the book later assembles is built from it. This section explains how braiding identical anyons is evaluated and why the R move needs a companion. Exchanging 2 identical anyons accumulates a phase, but which phase depends on the channel the pair fuses to. So the exchange operator is diagonal, exactly in the fusion basis, with eigenvalues written R carrying the 2 identical anyon labels A on top and the fusion channel C below. That is the whole move. R is defined only where fusion is Chernow. Braid a pair that isn't in a definite channel, and you can't read a phase off directly. Instead, you rotate into the basis where that pair's channel is sharp, an F move, apply R, then rotate back. Every braid of identical particles reduces to this conjugation, F, then R, then F inverse. The chapter hands you the second of the 2 generators. F changes which pair you can see fusing, R phases the pair you can. Together, they evaluate any braid. This section explains how anyons build a computer. A computer is 4 moves: get a state space, set it, transform it, read it. This part shows that anyons furnish all four, with the transform carrying the surprise. The fusion space of non-abelian anyons is the memory. Measuring a fusion channel initializes and reads. Braiding the anyons is the gate. What makes it topological is this. A braid's action depends only on the knot. Its world lines cut in space-time, not on where or how fast you move them. So a gate is quantized. You either make the braid or you don't. There is no 1% too long. For most non-abelian theories, such as Fibonacci, braiding alone is universal. Icing is the telling exception. This part explains why a quantum computation can be understood as a knot tied in space-time. You encode the information in the fusion channels of anyons, and you apply gates by braiding their world lines. The resulting unitary depends only on the braid's isotopy class, on the pattern of crossings itself, and not on the exact path your hand traced to draw it. Here is the step that does the work. A continuous control problem collapses into a discrete one. Tremble your hand in the middle of a braid and nothing changes. The gate is quantized because topological invariants ignore small deformations. Error, immunity here falls out of the representation itself. Once the operation is an invariant, its protection comes for free rather than being engineered in. But there is a boundary that reveals the deeper structure. Braiding buys this protection only where it also buys universality. Fibonacci, anyons, yes. Icing anyons, no. So topology guards the gates it can reach, and no. So topology guards the gates it can reach might want. This section explains what a planar diagram is at the level of structure. A planar diagram is the operator itself. The picture does not stand for a computation. The picture is the computation. Draw any one world lines that fuse and split, but never cross over or under, that begin and end in vacuum, and a finite rule set collapses the entire picture into a single complex amplitude. The value stays invariant under any deformation that neither cuts strands nor reverses a particle's direction in time, meaning lives in the topology, not in the accidents of the drawing. An object is what it does, transcribed into 2 dimensions. This is the braid-free fragment in 1 + 1 dimensions, a unitary fusion category. Pinning it down exactly is precisely what lets Chapter 13 add overcrossings and undercrossings and reach 2 + 1 dimensions. This section explains how a drawn picture becomes a piece of algebra. A drawn world line is a linear map, and that is the entire move. Read a planar picture from bottom to top. The lines entering are the bra, the lines leaving are the ket, so every diagram is an operator. Stacking 2 of them composes them. Capping both ends in vacuum collapses the operator down to a single complex number. Geometry becomes arithmetic. A finite rule set evaluates any picture. You may deform within causal isotopy, add or drop vacuum lines, split and fuse where fusion allows, and change basis by the eth move. Mach-Lane coherence makes the result independent of the order in which you apply them. Planar means no crossings, so the only events are fusion and splitting. What you have built is a unitary fusion category. Braiding and modularity wait for Chapter 13. Eng and modularity wait for Chapter 13. This section explains what a braiding diagram is and why its drawing is the computation itself. Draw the world lines of particles moving in a plane through time. Because 2 points in 2 dimensions cannot pass through each other, their trajectories weave. They braid. The strokes of a braiding diagram are the computation itself, not a picture of it. What the drawing computes depends only on the braid's topology, which strand crossed over which, and how many times. It never depends on the exact path, so smooth wobbles of the trajectory leave the answer untouched. That deformation invariance is the whole promise. The amplitude is read from the knot, from its topology alone, with the geometry discarded. Only in two spatial dimensions does over versus under carry meaning. Add a dimension and the strands unknot and the braid collapses to a mere permutation. This section explains how braiding completes the algebra of anyons. Braiding is the last local move. Planar diagrams already reduced a labeled tangle to a number through fusion with the F-move regrouping strands. Lift the picture from a plane into 2+1 dimensions, and world lines can now cross. Each crossing gets one new rewrite rule, the R matrix, the phase 2, anyons pick up when exchanged in a fixed fusion channel. The whole apparatus becomes a confluent rewrite system. Any knotted, labeled diagram resolves to one amplitude. Confluence is not free. It demands that the local moves commute, and that single demand is the hexagon equation, constraining R against F. Pentagon closed fusion. Hexagon closes braiding. Together they are exactly a unitary braided fusion category, the form every 2+1 dimensional anyon theory must take. On theory, must take. This section explains what it means to seek isotopy, to make your diagrams forget how a strand was bent. You want to pull any zigzag straight for nothing. The bare fusion rules refuse. Straightening charges you a factor of F. The whole chapter is a single move. Absorb that factor into a rescaling. Give each loop of particle A its own weight, D indexed by A, chosen, so the zigzag's cost collapses to a mere sign, plus or minus 1. The +1 you can gauge away is bookkeeping. The -1 that survives on a self-dual particle cannot be normalized off. That residue is the Frobenius Schur indicator, a genuine physical obstruction. The pattern, biasymmetry by rescaling the basis. Whatever will not rescale away is invariant. G, the basis. Whatever will not rescale away is invariant. This section explains why anyon world lines have to be rescaled to compute knot invariance and what the one sign that resists rescaling actually means. You want strands you can deform freely, a property called isotopy, because only a diagram that stays invariant under deformation computes a knot invariant. The naive rules refuse this. Straightening a zigzag leaves a factor of F behind. The move is to rescale the objects themselves. Give every particle loop a weight, D sub A, chosen to swallow that factor. What the rescaling can absorb simply vanishes. What it cannot absorb is a single irreducible sign, the Frobenius Schur indicator. That sign is a genuine physical fact rather than a defect. It is the shadow of framing. A world line is a ribbon rather than a thread. The lesson outruns anyone's. When a desired symmetry fails, renormalize to absorb the failure. The residue that survives the rescaling is the real invariant. This section explains topological spin, why pulling a twist out of a ribbon costs something. Pull a curl out of a ribbon and you cannot do it for free. A single phase, call it theta sub A, falls out. Read the ribbon vertically as a world line, and that curl is a particle turning once around its own axis. The phase is what Rotation in place costs. This is topological spin. The topological spin, theta sub a equals e to the power 2 pi I times h sub a, and it carries the whole of spin statistics. Integer h gives a boson, half integer, a fermion, anything between an anyone. You read it off one number. The step that does the work is this. Self, rotation, exchange, and braiding are one phenomenon seen from three angles. The twist is a strand braided with itself. Spin here is the topology of the world line itself. The standard picture treats spin as an internal label pinned to the particle. It is instead what the world line does when it turns once around. This section explains how spin appears in anyon theory when you thicken each world line into a ribbon. Promote every anyon world line from a string to a ribbon, and one number falls out. Theta A, the phase a particle pays to rotate once around its own axis. That is the chapter, spin, arriving in a theory with no spatial spin, recovered as the twist you cannot flatten away without paying. That phase, theta A, equals e to the power 2 pi a times h. Here is the step that does the work. This self-rotation phase is the exchange statistics. Braiding two copies and twisting one are the same ribbon deformation seen twice. This equality is the ribbon identity. Spin and statistics stop being two separate axioms and collapse into one geometric quantity. That is exactly why a flat diagram, blind to framing, could never have shown it. Framing is what makes the twist visible. This section explains what makes 16 of Simon's any-one theories, the easier kind, the ones with planar or three-dimensional isotopy. Take the general anyon diagrammatics of chapters 12 through 15, where deforming a diagram can incur non-trivial factors. Keep only the subclass where that friction vanishes, theories whose amplitude survives every smooth space-time deformation with world lines read as ribbons. Simon names this ribbon isotopy invariance and frames the chapter as the easier version. Here is the payoff. The diagram's value becomes a pure topological invariant of the embedded ribbon graph. Page orientation stops mattering, legs bend freely, and F moves to form arbitrarily. Planar is the 1 + 1 dimensional floor, with no crossings. The three-dimensional case admits crossings, resolved back to planar through the R matrix. The generative move is this. Impose maximal deformation symmetry, and what survives is exactly the topology. This section explains what happens to anyon calculus when you demand more symmetry from it. Demand more symmetry, and the calculus over the objects loses distinctions. That is the whole chapter. The general anyon diagrammatics of chapters 12 through 15 carried orientation as real information. Which way up was, which leg bent, which way, could all change an amplitude. Now restrict to the nice theories, the ones whose amplitude survives every smooth space-time deformation when world lines are read as ribbons, what is called ribbon isotopy, or regular isotopy, or regular isotopy. Under that restriction, orientation stops meaning anything. Rotation, reflection, turning legs up or down, all become gauge, so the rule book shrinks. F moves bend legs freely. The direction of the page is irrelevant, and the earlier axioms collapse to the shorter Leavenworth list. Constrain the theory harder, and the moves over it simplify. This section explains what further structure the axioms already contain. Nothing new is postulated here. The chapter only harvests what the axioms already forced. One diagrammatic move recurs throughout. Fuse two loops, then remove the bubble, as shown in figure 17.1. That single move proves the quantum dimension is the Perron-Frobenius eigenvalue of the fusion matrix. It builds the unlinking matrix, S tilde, and it fixes the modular S matrix. The surprise that does the work is the Verlinde formula. It reads every fusion multiplicity off the S matrix alone. The whole fusion algebra collapses into one unitary matrix, and that S matrix, together with the twist T, generates the group SL2Z, the mapping class group of the torus. So fusion, which is algebra, and torus diffeomorphisms, which are topology, are one and the same datum. The word modular names exactly the condition under which this coincidence holds. No transparent particle exists, but the vacuum, datum. The word modular names exactly the condition under which this coincidence holds. No transparent particle exactly the condition under which this coincidence holds. No transparent particle except the vacuum. This section explains what the chapter proves and why it posits nothing new. The chapter reads off invariants that the fusion and braiding rules already forced. That is the whole move. A topological theory's entire observable content collapses to a small packet, the quantum dimension, together with the modular S and T matrices and the central charge modulo 8. Every entry in that packet is a theorem rather than an axiom, something derived rather than posited. The quantum dimension you met 3 ways: as the growth rate of the Hilbert space, as the largest eigenvalue of the fusion matrix, and as a loop weight, is proven here to be one number. This is the book's toolbox chapter, and any yawn theory is what its modular data does. Measurement can touch nothing else, and everything downstream cites it. Does. Measurement can touch nothing else, and everything downstream cites it. This section walks through the simplest enneagon theories and shows why so few of them exist. An enneagon theory is solved for. You never simply posit one. Fix a fusion ring, which is the rule for which particles absorb into which, and everything above it is forced. The pentagon equation pins the F matrices. The hexagon pins the R matrices. The S matrix falls out on its own. The whole chapter is one crank, shown in figure 18.1, turned on the smallest possible inputs. The 2-element Z2 ring alone drops out the boson, the fermion, and the semyon. Ising fusion yields exactly 8 theories. Every abelian theory factors into 4 primes. The surprise that carries the chapter is the finitude. Consistency, not physics, does the selecting, so choosing the fusion rules already almost chooses the world. Take a bigger ring, turn the same crank, and there are still only finitely many completions. This section walks through the first worked example, built from the machinery of the earlier chapters. Everything in chapters 8 through 17 was a machine with nothing yet fed in. You fix the fusion rules, solve the pentagon equation for F, solve the hexagon equation for F, solve the hexagon equation for R, and read off whether the result is modular. This chapter turns the crank on the smallest possible input, one self-dual particle whose diagrams collapse to a loop gas, Z2. The move that makes the chapter matter is this. One fusion rule does not fix one theory. The consistency equations are polynomial, so a single input admits a small finite set of roots. Here, the loop weight D takes the value plus or minus 1, and each root is a distinct enneagon theory. The abstraction becomes generative only under instantiation, and this toy case already exhibits the pattern that governs every later example. The fusion rules underdetermine, the pentagon and hexagon select. Scion rules underdetermine, and the pentagon and hexagon select. This section explains how enneagon theories built from a discrete group turn into a problem in group cohomology. Take a discrete group, G. Let each any one world line carry an element G. Reversing a line inverts it. so G bar equals G inverse. And fusion is just the group multiplication. G times H equals GH. Because the product is always a single element, never a superposition, every quantum dimension is one. The Hilbert space never grows. The only real freedom left is the F matrix, and consistency forces it to solve the pentagon equation. Here is the surprise this chapter is for. That equation is, symbol for symbol, the 3 co-cycle condition. So the associativity data omega of A, B, C lives in the third cohomology group, H3 of G, with coefficients in U1. Classifying these any-one theories collapses into computing a cohomology group. A consistency polytope in one domain is a cohomology class in another. This section explains how a whole family of any-one theories drops out of a group by looking the answer up instead of solving for it. And each element of a discrete group, G, a particle, call the identity the vacuum, and let fusion be group multiplication. The whole consistency problem you would otherwise grind out by hand collapses into a catalog lookup. The pentagon equation, that constraint on the associators, is literally the 3 co-cycle condition. The F matrices you are permitted are exactly the third cohomology group of G with coefficients in U1, already tabulated by mathematicians. Physics inherits cohomology's bookkeeping intact, so you look up your any-one theory rather than solving for it. Here is the boundary that makes this predictive. Braiding needs the hexagon, and the hexagon silently assumes that A times B equals B times A. So abelian groups can braid, while non-commutative ones give a valid planar algebra, but no consistent braiding at all. This section explains how the distinction between bosons and fermions arises from the representation theory of the permutation group. Identical particles carry no label telling them apart, so exchanging two can act on the state only through the group that permutes them. What a particle is how that group represents. Bosons and fermions are the 2 one-dimensional representations of the symmetric group. The trivial one sends every swap to +1. The sign 1 sends every swap to -1. Statistics becomes a choice made inside the representation category of the group, written rep of G rather than a property glued to matter. The frame carries its own boundary. Fix the exchange group, and you fix the possibilities. In 3 dimensions, the symmetric group Sn is forced, and ±1 exhausts its one-dimensional part. That is precisely why Richter statistics must go looking for a different group. GI Richter statistics must go looking for a different group. GI Richter statistics must go looking for a different group. GI cases. This section explains what the any-yon formalism gives back when you feed it. Its most familiar input. Feed the any-one machinery that input, and it hands back the ordinary world. Take a finite group, G. Its irreducible representations become the particle types, and the tensor product decomposition theory, read diagrammatically, is the fusion rule with no new axiom added. The tensor product of representation, Ra, and representation Rb decomposes as a direct sum of representations, Rc, where each Rc appears a number of times given by the fusion coefficient NAB. The braidings it admits are exhausted by the trivial one, bosons everywhere, and fermions when a central element, Z, whose square is the identity, flips a sign. Every particle stays transparent and braids trivially with all the others, so rep of G is a symmetric category, the degenerate corner where statistics collapse to plus or minus 1. This is the null case, ordinary quantum statistics recovered as the formalism's most boring solution. This part explains how one deformation fixes the 2 things. A continuous group gets wrong about anyons. A continuous group like SU2 hands you infinitely many particle types and only trivial braiding, which is twice wrong for anyons. The chapter's whole thesis is a single knob. Replace every integer n in the representation theory by its Q-deformed counterpart, the Q integer n, a one-parameter bending of arithmetic that relaxes back to the ordinary. Theory n, a one-parameter bending of arithmetic that relaxes back to the ordinary. At generic Q, nothing structural moves and the tower of spin stays infinite. But tune Q to a primitive root of unity so that the Q-deformed integer k plus 2 equals 0, and the tower truncates to finitely many irreducible representations. The formerly trivial braiding is forced to become non-trivial to keep the hexagon identity satisfied. One deformation cures both defects at once. That machine is SU2 at level K, the source of Chern-Simons, anyons. This section explains why anyons force you to deform a Lie group, and what falls out when you do. A Lie group hands you infinitely many representations and only trivial braiding, the wrong raw material for anyons, which demand finitely many particle types and non-trivial exchange. So deform. Replace every integer n by its quantum version, the bracket n sub q, a function of a knob q that recovers ordinary n as q goes to 1. For generic q, nothing improves. Then tune q to a root of unity. The tower of representations collapses to a finite list, those with j less than or equal to k over 2, while the braiding becomes non-trivial, and what falls out is exactly the Chern-Simons theory, SU2 at level k. The primitive is deformation, then resonance, a continuous parameter, bland everywhere, made singular at one special value, where the forced degeneracy hands you both the finiteness and the structure. The rigid original could never give. I'll value where the forced degeneracy hands you both the finiteness and the structure that the rigid original could never give. This section explains how an entire any-on theory follows from fixing a single number. Fix one number, the value a closed loop is worth, call it d. Everything else, which particles exist, how they fuse, their braiding phases, is forced. That is the chapter's whole move. The Ennian theory is the free planar diagram algebra on that single scalar. Particle species are carved out of the algebra rather than posited as given data, each one an orthogonal projector, the Jones-Wenzel projector, on a cable of n parallel strands. Species Ni exists precisely when its n-strand loop value, dn, is non-zero, so the discrete theories are exactly the values of d at which the projector tower truncates. When d equals plus or minus 1, you get bosons, fermions, and semions. When d equals plus or minus the square root of 2, you get the Ising theory. Chapter 2's loop rule, read as a generator rather than a curiosity, is the anyons. This part explains how a single number generates an entire any-on theory. Assign a closed loop the value d and nothing else, and the full spectrum of particle types, their fusion rules, and their FNR matrices all fall out as forced consequences. The engine is the Jones-Wenzel projector. Particle n is the operator, Pn acting on n parallel strands, the one operator that every cap or cup annihilates. It is a type defined by what kills it, its identity fixed entirely by the caps and cups that send it to 0. New types keep appearing as long as the recursion stays non-zero. D sub n plus 1 equals d times d sub n minus d sub n minus 1, demanding that the algebra eventually close quantizes d to 2 times the cosine of pi divided by k plus 2. Ising, Fibonacci, the semionds, each is merely one admissible value of that single number, R. This part explains how a state sum topological quantum field theory builds a global invariant out of a purely local recipe. The construction manufactures a global topological invariant as a local statistical mechanics sum. Chop the manifold into tetrahedra, hang a quantum number on every edge, weight, each labeling by data read straight off a planar diagram, algebra, and sum over all labelings. The lattice is an artifact. That single demand fixes everything. Any two triangulations are joined by a finite set of elementary retriangulations. The Pochner moves, so invariance under those moves alone certifies that the sum reads the manifold and not the mesh. Here is the surprise. The chapter understates. A mere planar algebra suffices, no braiding, no R matrix, to build this 2 plus 1-dimensional topological quantum field theory. Topology is precisely what survives, forced blindness to the discretization. This section explains how a topological invariant of a 3-dimensional space gets built from purely local data. Chop the manifold into tetrahedra. Hang a quantum number on every edge. Weight each tetrahedron by a symbol read off a planar diagram, algebra, and sum the product over all labelings. What you get is a partition function in the exact sense of statistical mechanics. The number is a topological invariant for exactly one reason. Any two triangulations of the same space connect through a finite kit of local rearrangements called Pochner moves. So invariance under those moves is invariance under everything. And that local condition is nothing new. The 2-3 move is the pentagon equation. Here is the generative pattern. A global invariant is manufactured from a purely local weight, the instant that weight survives, the moves that generate all discretizations. The surprise is that a 2-dimensional algebra already suffices to build a 3-dimensional theory. This section explains how a topological quantum field theory invariant of a 3-manifold is built from a diagram you can actually compute. To assign a number to a thing you cannot touch, route through a thing you can evaluate a diagram link sitting in the 3-sphere. You cannot directly evaluate an arbitrary closed 3-manifold. So present every manifold as surgery on some link and let the manifold number descend from the link and lick the manifold number. Licorice and Wallace guarantee this presentation exists from the link number. Licorice and Yush's. The catch is the fiber. Many different links surge to the same manifold, and these links are related by Kirby moves. So the link invariant cannot be arbitrary. It must be constant on each Kirby class, a function that is well defined on the quotient. The construction that achieves this colors the surgery link with the omega strand, the Kirby color, and adds a framing phase. Once you do that, handle slide invariance, and blow up invariance fall out automatically. That quotient, descended number, is the Witten, Reshetikhin, and Turaev invariant. This section explains how to assign a number to a closed 3-manifold, an object you cannot evaluate directly, by routing the computation through something you can evaluate. The move is to number the untouchable by way of the touchable. You cannot score a closed 3-manifold on its own, but surgery presents every one of them as a framed link in the 3-sphere. Licorice and Wallace proved that this presentation is onto, meaning every such manifold arises this way, and a link is a thing you can evaluate. The redundancy is the whole move. Many different links surge to the same manifold, and those links are related to each other by Kirby moves, blow up and blow down, and handle slide. So a link number counts as a manifold. number only if it is blind to those moves. It has to be a function that descends to the quotient. To build that function, color the surgery link with the omega strand, the Kirby color, and attach a framing face. Kirby invariance then falls out for free, and the descended number is the Witten, Reshetikhin, and Turayev invariant. This section explains any uncondensation as a single generative move. Pick a boson, an any J whose self-braiding is trivial, meaning its topological spin theta sub j equals 1, and declare it the new vacuum. The entire theory then reorganizes around that declaration. That single move is modeled on Bose condensation, where a macroscopic population floods one state. It forces two consequences, the chapter names theory. First, identification. Anyons that differ only by fusion with J become indistinguishable. Second, confinement or splitting. Anyons that would braid non-trivially with the new vacuum cannot survive in it. With the new vacuum cannot survive in it. The generative primitive is a quotient. Condensation is the division of one modular theory by a chosen condensable boson, exactly as symmetry-breaking quotients a group by the unbroken subgroup. Bice and Slingerland named this topological symmetry breaking. Oceans a group by its unbroken subgroup. Bice and Slingerland named this topological symmetry breaking. This section explains the entire move behind condensing a boson. You declare a boson to be the vacuum, and everything else follows. Pick a particle J that braids trivially with itself, a boson, what the chapter calls a simple current. Let it flood the ground state. The new condensate then absorbs and emits it for free. Two consequences follow mechanically. The first is identification. Anything differing only by fusing copies of J becomes indistinguishable, so particles collapse into orbits of J, each written as bracket A. The label A stops being conserved. Only the orbit survives. The second is confinement. Anything that would feel J's braiding phase cannot coexist with the condensate, and is expelled. Read structurally. This is Bose. Einstein condensation lifted to anyons, a subquotient carrying one anyon theory to another. The chapter names it topological symmetry breaking. This section introduces quantum error correction and why it works at all. Redundancy is the whole trick. Spread one logical bit across many physical ones, so a local error surfaces as a visible disagreement you can vote away. This is the 3-bit repetition code. The quantum version looks doomed twice over. No, cloning forbids the copies, and measurement collapses the very state you would inspect. The chapter's thesis is that correction survives both anyway. Shor showed this in 1995, and it is surprising that it is possible at all. The way through is to measure only the disagreement between qubits, never their contents. That is the move the toric code will make geometric. Store the information in a global relation. No local error can reach, and read the error without ever reading the state. This is where the same move turns topological. This section explains how a quantum memory protects a stored state from errors, and why two facts that look fatal turn out not to be. Begin with the classical case. Classical memory survives errors by redundancy. You store 0, 0, 0 in place of a single 0, and if any one bit flips, you majority vote the original. Value back. Two facts seem to kill the quantum version. You cannot copy an unknown qubit, which is the no-cloning theorem, and reading a qubit collapses it. The whole thesis here is that both obstacles dissolve under one move. encode alpha times ket 0 plus beta times ket 1 as alpha times ket 0, 0, 0 plus beta times ket 1, 1, 1. Then measure only the relations between the physical qubits, never their values. The measurement of poly z on qubit 1 times poly z on qubit 2 asks whether qubits 1 and 2 are equal, without asking what either one actually is. These operators are called stabilizers, and they commute with the code space. So their eigenvalues, taken together as the syndrome, diagnose the error without touching the stored superposition. Shor's 9-qubit code shows the same equality check, run in 2 bases, catches every single qubit error. Correction is measuring what you must not read. This section introduces Kitaev's toric code. Kitaev's move is to hide the information where no single qubit knows it. The spins live on the edges of a lattice wrapped onto a torus. 2 families of mutually commuting checks pin down a ground space. The vertex operators measure the parity of downspins, a product of sigma z. The plaquette operators are a sigma x ring flip. What the degeneracy of that ground space counts is the torus's handles rather than the spins. That is the whole thesis and why the chapter sits in a topology book. An error-correcting code is a topological quantum field theory. ELF becomes the immunity, has no local address, so no local address, so no local error can read or corrupt it. Locality becomes the immunity. Every later mechanism, the anionic excitations, the anionic excitations, the anionic excitations, the anionic excitations unfolds from that single relocation. Every later mechanism, the anionic excitations, the code distance, unfolds from that single relocation. This section explains how the toric code stores a qubit in what no local measurement can see. Store the qubit in what no local measurement can see. The toric code fills a lattice with spins, then imposes 2 local checks everywhere. Every vertex must bound an even number of loops, and every plaquette must sit in an equal flip superposition. These stabilizers nearly pin the state, but not quite. The product of all of them is the identity, so exactly 2 binary choices escape, the parity of loops winding each cycle of the torus. That winding is global. No local error can read it or flip it. The protected information lives in topology, not in any spin, which is exactly why error correction here is a topological quantum field theory. Topological quantum field theory. This section explains how the toric code stops being a code and becomes a phase of matter. Promote a constraint to an energy and a code becomes matter. The toric code stabilizers, the vertex and plaquette checks you wanted pinned at +1, get summed into a single Hamiltonian, the negative of their sum. Now satisfying every check no longer means no error. It means lowest energy. The ground space is exactly the old code space, untouched. The rest is relabeling. A violated check, once called an error, is now a particle, a localized excitation costing a quantized amount of energy. The code's 4-fold torus degeneracy becomes a ground state count fixed by topology alone. That topological dependence is the tell. A commuting projector stabilizer code is a topological quantum field theory. Read from the Hamiltonian side is a topological quantum field theory. Read from the Hamiltonian side. This section explains how an error-correcting code turns into a phase of matter. Promote the stabilizer checks to energy penalties. So the Hamiltonian becomes minus the sum of the vertex operators, minus the sum of the plaquette operators. The error-correcting code now is a phase of matter. The code space becomes the degenerate ground state of a commuting Hamiltonian, and that single reframing is the entire chapter. What were errors are now particle excitations. There are vertex defects called E, plaquette defects called M, and their bound state called F. These live above the ground state at an energy cost of delta. Here is the surprise that makes the whole picture close. Topology alone fixes the counts. There are 4 ground states on the torus, and 2 to the power, 2G, on a surface of genus G, matching exactly the 4 particle types. It is the same object seen at 2 altitudes, a quantum memory from one angle, topologically ordered matter from the other. This section explains why topologically ordered matter resists local disturbance. Protection appears when the information distinguishing your states is global, yet every disturbance is local. The chapter makes a single claim. A topological phase's ground state degeneracy and its any-one statistics survive any small local perturbation. They split only by the ratio of J to delta raised to the power L, which is exponentially small in the system size L. Here is why. To tell 2 ground states apart, a quasi-particle must be dragged all the way around a non-contractible cycle, and a local operator moves it only 1 step, so the task needs order. L applications, each one costing J divided by delta across the gap. No finite product of local operators can resolve a topological difference. Topological order therefore belongs to the phase itself rather than to any particular Hamiltonian. This is why the toric code makes a robust qubit, ACE, not to any one Hamiltonian. This is why the toric code makes a robust qubit. This part explains why the information stored in a topological phase resists local perturbation. A perturbation is local, but the stored distinction is global, so nothing local can read it. The 4 toric code ground states differ only by whether a quasi-particle has been dragged all the way around a non-contractible cycle of the torus. The perturbation delta H, being a sum of local terms, can only move a quasi-particle 1 step at a time. To split the degeneracy, you must chain roughly L applications into a loop that wraps the system. That loop first appears only at order L in the expansion, so the splitting scales as J over delta raised to the power L, exponentially small in the system size. Robustness is a geometric fact, the distance a local operator must travel before it notices what the topology has hidden from it. No fine-tuning of the Hamiltonian is involved. Tice is what the topology has hidden from it. No delicate tuning of the Hamiltonian is required. This section abstracts the toric code into the Q algebra and shows how a single primitive generates its whole particle spectrum. Delete the lattice and the toric code becomes a gas of non-intersecting loops under planar skein rules. The generative move is this. A quasi-particle's charge is read from the algebra of loop states on an annulus, wrapping it never from the region's interior. This is Okeanu's tube algebra, whose multiplication glues tube algebra, whose multiplication glues tube onto tube. Its idempotents are the particle types. Written out, O, a composed with OB equals OA when A and B carry the same label and 0 otherwise. So a particle is exactly what its surrounding annulus measures. The interior holds nothing that names it. The whole spectrum falls out of one primitive, charge equals boundary algebra, particle equals idempotent. Feed that same recipe any pentagon, consistent diagram algebra, and it manufactures topological phases wholesale, worked through in chapters 31 through 33. This is the lattice's death. This section explains how the toric code becomes a diagrammatic object once you drop the lattice and keep only its equivalence classes. Forget the substrate, keep the equivalence class. That is the whole move. The toric code stops being a lattice model and becomes a gas of non-intersecting loops whose only law is isotopy, plus surgery, the same skein rules threading the entire book. A ground state is no longer a counted configuration, but an equivalence class under those moves. The 4 states on the torus are just loop parity across its 2 cycles. Once a phase is defined by its diagram algebra rather than its lattice, swapping the trivial d equals plus 1z2 rules for any pentagon. Consistent algebra generates every phase in chapters 31 to 33, and quasi-particles fall out lattice-free, which is what the tube algebra will classify. This section explains how the Kitaev quantum double model generalizes the toric code by swapping its alphabet. Start with the toric code. Each edge carries 1 spin, a 2-element label drawn from the integers modulo n. 2. Now, replace that alphabet with a whole group G, abelian or non-abelian, and the entire construction regenerates itself. The toric code was only ever the instance where G is the group of integers modulo n. Once the edges carry group elements, the 2 commuting projectors fall out of the group's own structure. The vertex operator demands that the ordered product around a site equal the identity. That is flatness, a discrete Gauss law. The plaquette operator averages over left multiplication by every element H in G. That is gauge symmetrization. Their common +1 eigenspace is the ground state, the quantum double of G. The non-abelian case is the payoff. Its defects braid, so storage becomes computation. This section explains the group-valued generalization of the toric code. Take the toric code and swap the number on each edge for a group element. That single substitution is the whole chapter. The 2 local checks survive intact, only reread. The vertex operator demands that the ordered product of outgoing labels be the identity, a G-valued flux conserved at every vertex. The plaquette operator averages over left multiplication by every H, a gauge identification of configurations. Their shared ground state is a topological quantum field theory, the quantum double of G. It is no longer sensitive to the lattice, only to the surface's topology. Abelian G merely rebuilds the Z encode. The payoff is non-abelian G, where braiding defects computes. The generative move, fix the constraints, promote the coefficient object, and later chapters promote it once more. Constraints, promote the coefficient object, and later chapters promote it once more. This section explains the doubled semyon model as a single reweighting of the toric code. Take the toric code's loop gas ground state and change one thing. Weight each loop configuration by -1 to the power of the number of loops instead of by +1. That single sign, the skein rule with d equal to -1 replacing d equal to +1, is the doubled semyon model. The Hamiltonian skeleton is unchanged. Same honeycomb lattice, same vertex term, only the plaquette flip now drags a minus sign whenever it changes loop parity. The bosonic charges of the toric code become semyons, particles that accumulate a phase theta equal to plus or minus I on self-encirclement. It is called doubled because both chiralities appear together, the left-handed and right-handed semyon theories, as a product. That pairing is exactly what keeps the theory achiral enough to live on a lattice, as a commuting projector ground state. The generative move is this. Twisting a loop gas is reweighting its amplitude by a cocycle. This section walks through a single sign flip that turns the toric code into a new topological phase. The doubled semyon model. Flip one sign and the toric code twists into a new phase. The loop gas that built the toric code weighted every configuration by D equals +1. Charge each loop operation with a minus sign, D equals -1, and you have the doubled semyon model. Nothing else changed but the signs of the plaquette term. The generative surprise is what the sign buys. A planar diagram, algebra records no-handedness, and braiding is extra data you never supplied. Build a loop gas from the semyon skein rules alone, and both chiralities emerge, left-handed and right-handed semyon, the group SU2 at level 1 times SU2 at level 1. The double is automatic, precisely because you refused 2 at level 1. This is the primitive that Chapter 33 generalizes. Discard braiding, keep the planar algebra, recover the Drinfeld double. This section explains the Levin-Wen string net construction as a functor from category theory to physics. Hand the machine a category, a planar diagram, algebra of string types and fusion rules, and it returns a two-dimensional lattice, Hamiltonian whose ground state is a topological phase. The construction is a functor, input structure, output physics. The surprise that drives the whole construction lives in the output's identity. It is always the Drinfeld double of the input, its own mirror grafted on, giving A cross A when the input is modular. A plane cannot carry chirality, so the machine symmetrizes it away by doubling. This is why toric code, doubled semyon, and the Kitaev models all fall out as single evaluations of one functor, Turayev-Veros TQFT, now wearing a Hamiltonian. Fusion category, in, its center out. Its center out. This section explains how a purely planar construction manufactures a theory that braids. Feed the machine only planar rules, how diagrams fuse, how a loop is worth its quantum dimension, no braiding anywhere. And it hands back a theory that braids. That is the whole chapter. The Drinfeld double manufactured from a spherical tensor category, its ground state, a democratic sum over every diagram reachable by the allowed moves. What emerges is the input doubled, one right-handed copy and one left-handed, A times A, carrying twist and braid data no one put in. The doubling is the tell. It never breaks time reversal, so you cannot get one chirality without its mirror. Toric code, doubled, semyon, and Kitaev all fall out as special cases. Here, the constructions of the last chapters converge. One construction, different inputs. Different inputs.